Temperature is the most measured value in process automation. The most common sensor technologies in temperature measurement devices are resistance temperature detectors called RTDs and thermocouples called TCs. Let's have a closer look at thermocouples. In the early 1800s, physicist Thomas Johann Seebeck discovered that heat applied to a junction of two different metals could generate electricity, a phenomenon now known as the Seebeck effect or the thermoelectric effect. A TC sensor is based on this effect. A TC sensor consists of two dissimilar metals joined at one end. This connection is known as the hot junction, whose temperature is finally indicated. At the other end is the reference point, the so-called cold junction. A temperature gradient along the thermocouple generates a small voltage in the circuit which can be measured and converted into a temperature reading. Now let's see how this voltage is produced. When one end of a metal wire is heated, the atoms in that region begin to vibrate more intensely. These vibrations transfer thermal energy to the free electrons, causing them to move faster and more energetically than those at the cooler end. While atomic vibrations scatter electrons randomly, the hot region still holds more high-energy electrons overall. This imbalance leads to a net drift of electrons from the hot end toward the cold end of the wire. As these energetic electrons migrate, the cold end starts to accumulate negative charge, while the hot end becomes slightly positive. This creates a small voltage across the wire. Let's look at why two dissimilar metals are needed to form a thermocouple. Each metal has a unique electron density and responds differently to heat. When the hot junction is exposed to a heat source, electrons in each metal gain energy differently due to their distinct physical properties. At the cold junction, this imbalance creates a voltage difference between the two wires. One becomes slightly more negatively charged than the other, and this voltage is what we measure. The voltage produced is not based on absolute temperature, but on the temperature difference between the hot and cold junction. To determine the actual temperature at the hot junction, we also need to know the reference temperature at the cold junction. This must also be measured. The easiest way to solve this is to place a temperature transmitter as the cold junction. Transmitters for thermocouple measurement include cold junction compensation. They measure the temperature inside the transmitter right at the terminals and use this value as the reference point. By combining the measured voltage from the thermocouple with the known temperature at the cold junction, the transmitter can accurately calculate the actual temperature at the hot junction and convert it into a standardized signal. Compared to the setup with a TC transmitter, using long extension wires made from the same materials as the thermocouple can be costly. Measurement errors can occur if the wire materials don't exactly match the thermocouple. There are various standardized thermocouple types, each defined by specific metal combinations, temperature ranges, and a unique voltage-to-temperature relationship. Due to their operating principle and materials, thermocouples can measure even the highest temperatures up to 1,800 degrees Celsius. They are extremely robust and suitable for harsh environments like furnaces, kilns, reactors, heat exchangers, waste incineration, cement production, and refineries.